Well, here we are with Chapter 19, Vibrations and Waves. This is our first video, description of waves. In this video, we're going to describe wave and wave behavior and learn a little bit about how we measure the speed of waves. Now, any repeating back and forth motion is a vibration. And a disturbance that's transmitted from one place to another with no actual transport of matter is a wave. So a wave is just a transport of energy. Light and sound are both forms of energy that move through space as waves. In this chapter, we're going to be focused on sound, and we'll be looking at light in the future. So here we go. Pendulums have been around for a really long time. If we take any kind of mass, like a stone or a hanging mass or anything, and suspend it at the end of a string, we've made a simple pendulum. Pendulums swing back and forth with such regularity that for a long time they were used to control the motion of most clocks. They can still be found in like grandfather clocks and a lot of cuckoo clocks. Galileo discovered that the time a pendulum takes to swing back and forth through small distances depends only on the length of the pendulum. The time of that back and forth swing is called the period, and it does not depend on the mass of the pendulum or on the size of the arc through which it swings. The size of the arc we call the amplitude, and the bottom of a pendulum, the mass at the bottom of a pendulum is called a bob, and when a pendulum just hangs naturally, that position we call its equilibrium position, and that pendulum will swing back and forth through that trajectory. The time that it takes to make one complete swing is called the period. And regardless of the mass of the bob, two pendulums of the same length have the same period, no matter what the mass of that bob would be. A long pendulum has a longer period than a short pendulum. That is, it swings back and forth less frequently than a short pendulum. So a grandfather clock's pendulum with a length of about a meter swings with a leisurely period of about 2 seconds, while a much shorter pendulum swings with a period that is less than a second. And we can see the way this affects the strides of certain people and animals. A person with a really long leg tends to have a slower stride than a person with short legs. So why are we talking about pendulums? I thought we were supposed to be talking about waves, right? Well, the back and forth motion, which is often called an oscillatory motion, the oscillatory motion of a swinging pendulum in a small arc is called simple harmonic motion. Now what we're looking at in these pictures here is a pendulum bob filled with sand. And what we see here is that when that conveyor belt is moving, we end up getting what's called a sine curve right here. When it's not moving, that pendulum bob will just trace out a straight line. And a sine curve is a pictorial representation of a wave. So that's why we're looking at pendulums here, is because we can get a picture of a wave by using a pendulum. Now we can also get simple harmonic motion if we were to place a mass at the end of a spring and allow that spring to oscillate up and down. If we were to attach some kind of a pen or something to that bob, then it would trace out a sine curve. A sine curve is just a pictorial representation of a wave. So in a wave, the high points are called crests, the low points are called troughs. The distance from an equilibrium position is called amplitude. And then the amplitude is the maximum displacement then from that equilibrium. The wavelength of a wave is the distance from crest to crest or trough to trough, or really from any one point to any other one point at the same level on that wave. So because a wavelength, it's a length, we're going to measure that in meters, right? In units of meters. So if your water waves from the beach would be measured in, long meters, whereas pond ripples would be measured in centimeters, and light waves are measured in billionths of a meter. We can also talk about wave frequency. The frequency is the number of vibrations an object makes in a unit of time. The frequency specifies the number of back and forth vibrations then in a given second. So a complete back and forth vibration is one cycle. If a vibration occurs in 1 second, the frequency is 1 cycle per second. If 2 vibrations occur in 1 second, the frequency is 2 cycles per second. The frequency of the vibrating source and the frequency of a wave it produces are the same. And we have to be clear about frequency, the difference between frequency and speed. A frequency is how fast a wave vibrates, and it's different than how fast a wave moves from one place to another, which would be the wave speed. Now, the unit of frequency, called the hertz, which is named after Heinrich Hertz, who demonstrated radio waves back in 1886. So 1 vibration per second is 1 hertz. 2 vibrations per second is 2 hertz, and so on. Higher frequencies are measured in kilohertz, and still higher frequencies in megahertz. For example, AM radio waves are measured in kilohertz, and FM radio waves are measured in megahertz. Radar and microwave ovens operate at gigahertz frequencies. So a radio station at 960 kilohertz on the AM radio, for example, broadcasts radio waves that have a frequency of 960,000 vibrations per second. A station at 101.7 megahertz on the FM dial broadcasts radio waves with a frequency of 101,700,000 hertz. These radio wave frequencies are the frequencies at which electrons are forced to vibrate in the antenna of a radio station's transmitting tower. The source of all waves is something that vibrates. The frequency of the vibrating source and the frequency of the wave it produces are the same. Now, just like the period of a pendulum is the time it takes for one back and forth swing, the period of a vibration or wave is the time for one complete vibration. And if we know the frequency of a vibrating object, we can calculate its period and back and forth. So suppose, for example, a pendulum makes 2 vibrations in 1 second. Its frequency is 2 hertz. The time needed to complete 1 vibration, that is the period of the vibration, is half a second. So as we can see from here, the frequency and period are inverses of each other. And often what we'll do is we write these in symbol form, right? So a frequency is equal to 1 over the period. Period was capital T because it's the time for 1 complete vibration. So period then is the reciprocal of the frequency. So most information about our surroundings comes to us in some form of waves. It's through wave motion that sounds come to our ears, light to our eyes, and electromagnetic signals to our radios and television sets. Even this information that you're getting in this video is coming to you in the form of waves. So it's through wave motion that energy can be transferred from a source to a receiver without the transfer of matter between 2 points. And that's really a big point about waves. When energy is transferred by a wave from a vibrating source to some receiver, no matter is transferred between the 2 points. Only energy is transferred between the 2 points. A simple way to think about this is if you were to take a string and shake it up and down. Each part of the string moves up and down, and the disturbance moves along that string, but not any part of the string itself moves along. Okay? If you drop a stone into a pond, you can get water waves to propagate out from that disturbance, right? It's the disturbance that moves, not the water. If you've ever seen, a duck sitting on the surface of water as a wave passes under it, the wave passes under the duck stays in place because it's the energy that's moving under the duck as that wave passes by. Now, just like water waves, right? When somebody speaks to you from across the room, a sound wave is a disturbance of the air that travels across the room. The air molecules themselves do not move along. It's the energy that moves through that air. The air, like the rope and the water in the previous examples, is the medium through which wave energy travels. Energy is not transferred by matter moving from one place to another within the medium. So the speed of a wave depends on the medium through which that wave moves. And whatever that medium is, the speed, the wavelength, and the frequency are related. Take, for example, the water waves passing this pole here. If the wavelength is 1 meter, and 1 wavelength per second passes the pole, then the speed of the wave is 1 meter per second. This tells us then that if the wavelength is 3 meters and 2 crests pass a stationary point each second, then 3 meters times 2 waves pass by in 1 second. Then the waves therefore move at 6 meters per second. This gives us an equation here of V equals wavelength times frequency, where the V is the wave speed. This symbol lambda is a wavelength, this is the Greek letter lambda, and F is the wave frequency. And this equation here is called the wave equation, and it's very important when we're dealing with waves. It's from this wave equation that in air, the product of wavelength and frequency is the same for every frequency of sound. That's because sound waves all travel at the same speed, which is 343 meters per second. This is why we don't hear the high notes in a chord before you hear the low notes. The sounds all reach you at the same time. Long wavelengths have low frequencies, short wavelengths have high frequencies. So wavelength and frequency vary inversely to produce the same wave speed for all sounds, as shown in this table here. So let's take a look at the wave equation used in an example. If a water wave vibrates up and down 2 times each second, and the distance between wave crests is 1.5 meters, what's the frequency of the wave? What is its wavelength? And what is its wave speed? Well, based on the definition for frequency, the frequency is going to be 2 hertz. It vibrates up and down 2 times each second. Its wavelength, as given from the problem, is 1.5 meters. To figure out its speed, then, we take the wavelength times the frequency, and we get 3 meters per second. We'll see questions like this and others in class. See you then.